If you like, Slava, we can start.
Yeah. Let's continue our session. The second speaker today is Olaf Post. The title is Different Variants of Generalized Operating Norm Convergence. Please.
Yeah, thank you very much for giving me the opportunity to talk here today. And as I already said, I have to apologize that I didn't attend many talks before because we still have school holidays here and I was just away with my children. Okay, so title is, I would like to talk about a convergence of operators if they act in different spaces and they're actually different versions of doing this. This talk is mainly based on joint work with my current PhD student, Sebastian Zimmer, and some older results from my former PhD student he finished in 2020, Jan Zimmer. So I will give some motivation of why one needs a generalized convergence, and then some motivation, and then I give the definition, two concepts. And then I will tell a little bit about the first main result that these concepts are actually equivalent. And on point 4, I would like to say something about we defined using this notion of convergence, we defined some sort of distance or metric or quasi-metric. And I will also tell about related results to it. And finally, some outlook. Okay, so as a motivation, let me see, where's my cursor here? Okay, we would like to consider Laplace operators on domains, say something in R2 here, X with the boundary, or it could be some manifold. If you know what it means, you have the surface here, you can define some Laplacian on it. And well, as we know, I don't have to tell much about it here. Laplacians can be used to describe some waves on such a space. Could also be non-compact, by the way, yeah. Or you could describe the heat conduction on such a space. And one is mostly interested in the spectrum of such a operator, for example, the eigenvalues, as they describe some frequency of the waves, or the second non-zero eigenvalue would describe the heat conduction speed, and so on. And actually, I have 2 points of view. Point A is I have a simple problem and I have a perturbation of it. So the limit is a simpler object. I would like to know what is my perturbation is a more complicated object than a simple one, and B is the other way around. The approximation is simpler, and my limit is more complicated. And the question is, how is this behavior of the spectrum in both cases related with the approximation and the limit under perturbations? Well, a very natural question. So the mathematical formulation now, in my talk, I write delta n, and don't worry because I know some people use minus delta for the Laplacian, but my deltas are always non-negative. In the Hilbert space, Hn, typically this is an L2 of some Xn, of a domain, manifold, or whatsoever. And the operators are typically unbounded. And n runs through all the natural numbers, and for the limit I use the symbol infinity. So how would I now define delta n converging to delta infinity? Well, first thing is these operators are unbounded, or typically unbounded, and then we use resolvents. So for example, if the operator is non-negative here, -1 is not in the spectrum. sorry, there's a mistake here inside. I see this should be not bijektiv, it's actually German version. Sorry. Anyway, so I think most of you know what the spectrum is, of course. Yeah. So -1 is not in the spectrum, and as this operator is non-negative. So I can define the resolvent, -1 is +1. And this is a bound operator in the Hilbert space. Yeah. And I define now the convergence for these unbound operators just if their resolvents converge. In one fixed point, say -1. If it converges in one point, you can also use another one, which is in all of the resolvent sets. So how is it defined? Well, the norm resolvent convergence is just defined if the resolvents converge in operator norm. Yeah, the uniform convergence here. Sub over, you plug in f's and divide by norm of f. And this should be smaller than some delta n. And I will refer often to, in this case, to the convergence speed. Yeah. In most books like Reed Simon and Cato, they're not interested in how fast something converges, but I would like to keep track of this, of the convergence speed. And there's a related version, strong resolvent convergence. Strong means here pointwise. So if the resolvent, plug in a function f in the common space here, and this converges in the Hilbert space norm. Okay, this is nothing new to you, I hope. So here is a reminder here. Consequences. Well, in norm resolvent convergence, we have, for example, that suitable functions of the operator, like the heat operator. So the function phi t of lambda is e to minus t lambda. This would give the heat operator. Or I could plug in the spectral projection. If the boundary doesn't lie in the spectrum, I have to take care a little bit here. Well, you have convergence of this again in operator norm. And what's also more interesting about norm resolvent convergence, you have convergence of the spectra on compact intervals. Or you can formulate like this: a point is in the limit spectrum if and only if there exists a sequence of points in the approximating spectra that converges to lambda infinity. And you can also show the convergence individually for the discrete spectrum, including multiplicity, and the essential spectrum. This is all result, well, you can check up in these books. This is standard classical results, yeah? Okay. So strong resolvent convergence, well, then you still have convergence of operator functions. Here the class can be a bit larger, but the same class as before. But here we only have for the limit spectrum, a point in the limit spectrum, then there is an approximating sequence, but not the other way around. So what might happen that your operators here have a larger spectrum than the limit spectrum. It can suddenly shrink. There's a famous example in Reed Simon's book, okay, and others. And also convergence of discrete spectrum here. Yeah, I said that the spectrum can suddenly collapse. And this is sometimes called spectral pollution because you might have an approximation of your problem, and you might have eigenvalues which have a limit point here, the sequence, but which is not in the actual problem you want to consider. So this is my talk will basically be on norm resolvent convergence or some generalizations. The strong convergence concept I will give in the outlook maybe some discussion about it. So what do we do now? If here you see we always have all operators act in the same Hilbert space. But it's very often, especially if you talk on Laplacians on some spaces where the domain varies or where the manifold changes, what can you say then? How can you define then some reasonable notion of convergence? Okay, I would give you first some examples. I think some of you maybe have heard me talking before on this topic, so this might be not so interesting for you. But for those who have never heard about it, maybe I just start with some results. So the first one is actually together with Pavel Exner. We started working on this. This is why I developed this machinery here. The question is, you have a metric graph here. I hope you can see it. It's a bit tiny, but maybe a second, I just do a bit larger here. So, okay. So you have a metric graph, you consider the edges as intervals. So you have a function, L2 function on the interval, and you consider some conditions on the vertices. And the operator acts here as minus second derivative, like a Laplacian would do. And you need here some conditions. Sorry. Where's, I should make it smaller, sorry. Yeah, no. Sorry. Okay, I do it again as another picture. Good. And in order to turn this operator self-adjoint, I don't go into details here. If you're interested, I can give you some references later. You need continuity, and the sum of the derivatives should be 0. So some sort of generalization of Neumann conditions. Well, and then you ask yourself, if you're in a physical situation where, for example, you have a certain thickness here, like it's not 0 the thickness, but epsilon, or you have some tubular neighborhood here, like you could think of this as a surface here, or you could have a 3D space with boundary, whatever you want. If you have boundary, you take Neumann Laplacian here for some reasons. And the question is, if you shrink this epsilon n to 0, do you end up with a Laplacian here? And actually, yes, you do. This is here our results, or many of the results in different complexity with Pavel Exner. Actually, I have to mention that first Peter Kutschmann and a student of him, saying they worked on it also. They showed conversions of eigenvalues. Okay, sorry, I think I can only change page. So, like this. Okay, next one is just, well, don't bother too much about the details here. I just put some pictures from the papers. But what we did here is we have a space x epsilon, which is just a line, a cylinder size epsilon, and here infinity long, and some rectangle, a small one here, and you have some orders here, certain scaling. This scales much faster than this one, and a function in the limit is actually on the line only, because everything shrinks if epsilon goes to 0 to just a line as a space. And here you get some delta interaction, which means the difference of the derivatives equals some constant of the value. Your function is continuous. And the gamma is actually hidden here as so the gamma here, gamma epsilon squared, and this is, I think, epsilon to the power beta. This was some work with Andrei Chabostovsky. Well, okay, and again, you see in both cases here, you see the spaces actually change, yeah? I mean, definitely here, this is a 2-dimensional space or 3-dimensional space, and here this is 1-dimensional, and here the same. And also, you might, but if you never heard about metric graphs, quantum graphs, you can imagine that solving eigenvalue problems on this graph is much simpler than solving it on this PDE case here, this complicated structure. And similarly here, yeah, this is much more complicated than this one. Here, this is, you can just actually solve it explicitly in most cases. Okay, sorry. Another one is, oops, sorry, it's too large. Homogenization. Oh, sorry. Homogenization. It's again a work with Andrei Chabostovsky, an older one. Well, those of you who had already lots of talks about homogenization, what we did is we showed norm-resolving convergence in some sense. So we have automatically spectral convergence, and even also for non-compact spaces. Yeah, this is drawn compactly here, but it could be non-compact, no problem. And what we do is we have here small holes, which are periodically arranged inside some bounded or some domain, bounded or not. And the scale here is epsilon of the periodic cell, and the diameter here is some power of e to beta. Beta is some constant here. Some critical exponent. D is the dimension. Take the Dirichlet Laplacian, and here you can show that this converges to a Laplacian here plus some q. Some, I think it was called unusual term in the first time. And the q is actually, again, here the proportion here coming here. And again, you see the spaces change here. Here's maybe a little bit different because here you might think of, okay, this is x epsilon is a subset of x0. Or more precisely, I should talk about x epsilon n, and then this would be infinity here, yeah? But well, this is just a minor modification here of the notation. Okay. In all these cases, you need some sort of okay, again, in all these cases, the limit problem is some sort of simpler problem you can imagine. Here also is a Laplacian on a normal domain, and here it has a lot of much more complexity. Actually, if epsilon goes to infinity, the topological complexity gets much more complicated. Okay, so if anyone has some comments, or because I can't see the chat now, just let me know, yeah? Just shout or do something, yeah? Okay, next B, case B, where the approximation is simpler than the, well, in some sense simpler than the limit problem. I consider here some sort of discretization. Hn is some little L2, so discrete space with some point measure here, some weights on Xn is some discrete set or finite set. And the infinity space is just some L2 of some X infinity. This very simplest example is just the interval 0, 1, which is of course not too complicated. But if you think of discretization as a simpler problem, then you can imagine that Hn, now you divide the interval in 2n points plus 1 points, and then, yeah. Discrete, and then you consider the discrete Laplacian. Well, you take the value of the function minus its value as neighbors and some renormalization factor. And the limit operator would be the Neumann Laplacian, the usual continuous one. And actually, this is a very baby example for more complicated structures as fractals. And here, I guess you agree that this so-called Sierpinski gasket here, it's much more complicated than its discrete approximation. Again, here you have Laplacians on discrete Laplacians of the similar structure here on the with some weights inside on the vertices, and you can also do something on this pentagon. Yeah, and what you actually do is you repeat the structure and put it here and here, and then you take it again. You take this one, make it small, and put it in each 3 copies here, and this you do infinitely many times, and then you get the limit space. And similarly here. This is known in the community of fractals, so-called cross-critically finite fractals. And well, we entered in the subject because we showed also some resolvent convergence. I will come to it in a moment. No, so actually what we have shown that these discrete Laplacians, they're actually finite operators. They converge to the resolvent of this Laplacian here, which is again an unbounded operator. And this was known by these people in special cases, by symmetry and something, but not really in full generality. And the method I will show you in a moment shows that it works fine. This is, by the way, work with my former PhD student, Jan Zimmer. We have several papers on it. Okay, I have to look at the clock. Yeah, okay, I don't have so many slides, so it should be fine in time. Okay. Let me now come to the concepts and explain to them and motivate them by two examples. The first one is domain perturbations. Yeah, so you think of Xn is a subset of X. For example, X is a subset of Rd, could be, yeah? And maybe has some smooth boundary. You can weaken this assumption, it's only here for simplicity. And n is again the approximation number and also the limit for infinity. And we have some sort of limit. I don't want to go into details here. This would be an own topic of a talk. Let me just do I want to explain the concept of convergence and how to define and not exactly under which generalized this holds. We consider directly Laplacians. Again, we call that my Laplacians have this sign convention, Xn. How do we then define this convergence, yeah? Or convergence of the resolvents because they might be unbounded. Well, there's a very natural concept here because my Xn, everything here is subset of the same space and the same measure. This is important, yeah? Let's say Lebesgue measure, for example. Yeah. And then we can embed the approximating space Hn into H, which is the L2 of X, by just extending the function by 0. Very natural. The adjoint is then clearly you take a function of the big space and you restrict it. And now Weidmann, this is, well, actually we found it in Weidmann's papers. And I think this was basically Weidmann's motivation, Joachim Weidmann. He defined what he called generalized norm resolving convergence. We put Weidmann here because we have another one later. If and only if you take the resolvents and you put everything in the big space. B of H is the bounded operators on H. So you come from big space, restrict it, take the resolvent and extend it by 0. And the same here. And you want this to converge. And this is a very natural generalization because if you put spectral parameter here, then these operators still fulfill the resolvent equations. They just have a non-trivial, might have non-trivial kernel. Yeah, they are also called pseudo resolvents. And we will later call this common Hilbert space parent space. If you look in Weidmann's papers, you will not see our iotas here. You will just see some projections because he doesn't really make difference between these embeddings. He doesn't have a symbol for it and the projections here, but we found it useful to use this notation here. The simplest case is, of course, if, like in the homogenization case, if our approximating space is subset of the limit space. And then we can just use as a parent space the limit space, yeah? So this is very simple. And for this case, of course, I think this is done in many papers. You don't have to develop some abstract nonsense theory. It's just, you do some natural thing. Okay. And now, so this is now the first definition here. Okay, I will define it later a bit abstractly, but this is one thing how you can define, here, how we define it if it's different spaces. If you have main point here, everything is embeddable in a common Hilbert space. Yeah, like because the measures are the same and everything is here subset of a common space. But we've seen examples where the nature of the approximating space and the limit space are very different. Like the discrete subset of X infinity interval or Sierpinski gasket. Here, let me just give, for those who have seen it before, let me explain how we do. Actually, we define the Laplacians usually via their energy form, which is just the difference of the neighbored vertices squared and some weight here. And the limit energy form is just the gradient, which actually here the derivative, simple one on the interval. And the weight is just 2n for intervals. And the main point is here, actually what we do, how do we embed the discrete space into the continuous one? The main point is we use a partition of unity of functions here, some tent function, which is 1. This is 1 psi here, psi nv. And if you take another one here, for example, here, then you can see, oops, they add up to 1 here, yeah, and so on. For each vertex. And now this is terminology of Chauvel. You take the discrete space into the continuous space by just taking the value at the vertex and times this corresponding function. And as we have here functions which are also in the domain of the limit form, because this is a Lipschitz continuous function, it's in the H1 space here. We also have automatically that we don't have to smoothen something here. Okay, this is for let's say some function, the blue points are maybe the discrete function here, and this is just a linear interpolation, just a spline of order 1. This is a smoothing, and the discretize the other way around. The adjoint you can calculate is just you take a continuous function here, and now you take this corresponding tent function, take the integral, so somehow the screen area here, and you normalize it by some weight. Actually, where do I put? Yeah, actually, this is here. It's not so important. The details now. This is just the integral of such a function here. Yeah. Okay, and now the question is, how close is Gn close to a unitary operator? Yeah, and this is now the key for my next definition. Sorry. This is again repetition here. My J was a smoothing operator. J star was this discretization, just sampling your function and take some weighted samples. And how close is Jn to unitary operator? First of all, this is a partition of unity. And so you can write fv as where you just simply put this function inside here, the integral here. And you see, this is the integral here. This is the integral of the function. You can see the v prime, you can put it actually inside here. Then this gets a 1. So you just have here now this mu n of v, and you see it just collapses everything. So it's just the same, yeah? And now if you first smoothen and then discretize, you get a formula here, you can check. And if you compare it, how close are you to your original function? Smoothing, discretizing, you get something like this. And actually, if you look closely here, it looks a bit like the energy form, the discrete one. So actually, you can estimate it by some constants from the model, and actually this converges for the interval here, for example. Okay. This is actually just motivation why I'm interested in actually in these operators here. Identity minus J star J. So sorry if I don't go too much details of the examples because I would like to motivate it, but not go too many have too many details in the talk. And now I come back to the general concept. We're again in the Hilbert space setting, so no concrete spaces here. And I say that my operators converge in the QUE sense. Sorry, QUE stands here for quasi-unitary equivalence. Yeah, and not for some other things in physics. No. If and only if there's a bounded operator Jn from Hn to the limit space H infinity and some sequence converging to 0, such that, well, recall this was a smoothing, discretizing. In the first example, this is the other way around, discretizing, smoothing. And I want this, so I compare these operators, how close they are to unitaries, but not only an operator now, but I allow here some resolvent, which smoothes out a bit at high energies. And here's the same. And of course, I have to compare the operators. And there's a natural way, because my Jn goes between the two spaces, this is a natural way of doing it. And if 1 and 2 hold, I also sometimes say that these two operators are delta n quasi-unitary equivalent. Why the names? Oops. If delta n is 0 in 1 here, if this is 0 and this is 0, then actually this should be equal, yeah, so 0, which means Jn is a unitary operator. So, and then without loss of generality, I can assume the spaces are the same and Jn is identity. And then the second one just reduces to classical norm-resolving convergence. So this generalizes norm-resolving convergence in this sense. And why there's this unitary equivalence inside? Because this is just a quantitative generalization of unitary equivalence. Why? If delta is 0 here and here and here, then again, this is unitary. And this means here, these are also equal, these operators. So like this. And this means if this is unitary, that these operators are unitarily equivalent. Yeah. So what I have is a quantitative generalization of unitary equivalence. And my delta n measures how far I'm away from being unitary equivalent. Okay. Now, well, this is most of you already known. Again, the definition here, as I said before, repetition, and we have consequences of it. As for the classical norm-resolving convergence, I can take functions of my operator and suitable sandwich operators of the limit operator. and this all converges. I can even control the order for good functions, and the spectrum converges. This is also important as before. By the way, the same holds also for Weidmann's convergence. I didn't mention it here. Same conclusions in a similar way. And in particular, I have no spectral pollution for this convergence. So my limit points are exactly those which are, as points in the limit spectrum are those which are limit points of my approximating spectra. One thing is a disadvantage of the norm-solving convergence. If I would have here delta n, some compact exhaustion of a non-compact set and some Laplacians on it with a discrete spectrum, then I cannot have this convergence, because if I have a central spectrum here and a central spectrum is preserved or converges, this cannot be true, because here's no essential spectrum, here is a central spectrum. So these kind of examples do not work with my general setting. Okay, now both concepts together. This I did before. This is QE convergence with this identification operators, I call it sometimes JN, these conditions. And now let me repeat or define again what I call Weidmann's convergence. You can also refer to Sabine Böckli's paper and her PhD thesis. She worked a lot on this also. So I will call also the speed here, which is the upper estimate of the norm. So I say they converge in Weidmann's sense if and only if there are isometries into some common Hilbert space. H is missing here, such that the sandwich resolvents converge. As I said, Weidmann formulated it only for subspaces, so it looks a bit different in his articles, but yeah, we need to use precise notation here, otherwise it's hard to give some reasonable proofs. Interesting now, if you look at these two conditions, I mean, I learned about this this Weidmann concept actually very late at a talk from, I think, from Sabine Böckli. And first off, it looks quite different, yeah. Well, he named it generalized normal solving convergence, Weidmann, and in my old papers I also called it something like this, related. But interestingly, the concepts are equivalent. And this is now work of my second PhD student, my current one, Sebastian Zimmer. Here, because this is QE convergence here, repetition, and here the Weidmann conversion, and we use Dn for the sandwiched resolvent in the common Hilbert space, this parent space. And we have now the convergence in Weidmann sense if and only if convergence in the other sense. And now we have, let me briefly go to this here, not too many details, but there's a simple direction. If you have Weidmann setting, you want to show this QE setting, this quasi-unitary equivalence convergence. Well, this is quite easy here, because what you do is you have your Hn, you have some H, your In, and now you have an H infinity. You want to go back here. What you do here, you can actually take the adjoint of it. So there's a natural operator here, which is just this one here. Infinity star iota n here. And then, well, you have each isometry induces an orthogonal projection in the upper space here. And you take the orthogonal complement of it. And now you can do some calculations. I'm not going into details now, but what we do have, we have to show that this converges, yeah, because we want this setting here. This is Dn. So we express Dn plus some other things in terms of operators we know already the norm of it, yeah, like this one and this one and this one. Actually, what we use here is the fact that if you have Pn orthogonal iota n, if this comes together, you have 0, yeah, because yeah, you can easily check. This is why we have only, here's Dn has 2 resolvents, but only 1 remains, and it's the same here. Only here the resolvent both remain. And now we take the operator norms here on both sides. So we can estimate the operator of this by norm of dn, because all the other operators have norm 1. And so we have, if this converges with the same convergence speed. This is rather easy. Yeah, you see it, this delta n, well, as I said. Okay, now the complicated direction. What do we do here? The main difficulty here is, I mean, in Weidmann setting, you need the common Hilbert space, yeah? So, and now we start with just Hn, our Jn, and H infinity. But how do we find a space here? Yeah, and we have some isometries here. That is factorized. Yeah, like, this is totally unclear. So this will be, I will tell you in a step 3 later. Maybe you can take something home as a message. Maybe to learn something a little bit. A tiny inequality we learned here actually. First, what we do is we write dn in terms of these projections, and we have here only 3 terms because the 4th term has 2 signs, orthogonal signs here, and then from each side, there's a corresponding iota n, iota infinity, which cancels them. So only 3 terms. And now we have to express this in terms of, this is the things we know now. Okay. So if we have now isometries, yeah, that factorize it. Then necessarily Jn has to be a contraction because these are contractions, so the norm cannot be larger than 1. Then there are some calculations where you can actually write this in operator by some operator calculus, the square root of this operator here. So this is then smaller than, well, you can estimate this by delta n, so you get the square root here. And the other one is similar. And here the one for the resolvent difference. This is quite easy here, equality here. You see over here we lose some conversion speed. Yeah, I will talk about it later. So step 2, then it's fine. Now, how to factorize this operator? So recall we have Hn here, Jn, H infinity, and we have to find a common space such that we have an Rn here and a co-isometry, so a joint of an isometry, such that this factorizes. And the funny thing now, this is really the key observation here. So I never heard about before. So there's what Nudge called the defect operator. You take, so you need a contraction, otherwise this is not non-negative here. Take identity minus j star n jn, take the square root of it. This is what they call defect operator. Has nothing to do with defect indices. Yeah? This is just the other thing. And why do we do this? Well, now we have Jn. So I just calculate Wn squared. So I bring 1 square root on one side. So I get id n minus jn squared jn. Sorry, my handwriting is very bad. Fn. And now you see this is just 1 fn squared minus, and you put this on the other side, jn fn squared. So you just get this equality here. And this is very good. Yeah. Forget about the second one. Well, okay, this is well, this shows a little bit some formulas I used before. But this is the important thing here. Why do we do this? Well, now we have this formula. And then we said, as a Hilbert space, common Hilbert space, we take the Hilbert space sum of all Hns plus the limit space. Let me write it in the first component here. So the infinity isometry is just puts it in the first component. By the way, if I put iota n just component in the nth component here, then we would have totally not related components. So we will never expect any convergence the last condition. So we need to somehow split it around. So we put Jn here and this defect operator here. Well, now it's easy. This is isometry clear. And this is isometry because of this here. Yeah. Just check this formula. You take the orthogonal sum here, Pythagoras, square root of this norm, square root norm of this equals Fn. So isometry. And also, what does it mean, J infinity star? You just take the first component. But the first component of my Jn is just this one. So we have this formula also. So we factorize Jn. Yeah. So this is a construction how to construct a generalized in a general setting parent space. We need actually we need smaller than 1. If this is not fulfilled, you can actually rescale your operator. Some technical details I will leave out. This is not a really restriction. Okay. So let me just come back to show you the proof again. Sorry, yeah. So now we have the easy direction. I've showed you this one is clear. And the other one we also have roughly seen how it works. Yeah. So the main idea is actually here, this operator to do this. And this factorizes your Jn. Okay. Now I have to come. No, still some minutes. Okay. We've seen in the talk that actually we had some equality with this quantity here. So what we do now, we define a modified, so the M for modified here, QE convergence here, by taking this expression instead of just without the red part here. It's the same for the other one. And actually the convergence I showed you before, QE implies this one. This is easy to see, but you lose some speed. And actually what's interesting here, if you write this condition pointwise as an estimate, it's equivalent to Fn norm squared minus Jn Fn normed squared. This is actually no negative because it's a contraction. This is smaller than delta n squared and times the graph norm of Fn. You can check this is the same, yeah? Equivalent for all f in the domain of the operator, and similarly here. And sometimes you get even better estimates in problems. So before I only used the old version, and then this seems to be not the right one. This seems to be much better. Okay. Let me briefly mention something about other concepts of convergence of Rhine spaces. I'm very short here only, and I apologize for those who worked on these topics and if I didn't mention them. There's a lot of work done in homogenization theory, but let me say, basically, these convergence are some sort of strong resolving convergence, which means, oops, where's my cursor? Yeah, here. Which means I have some pointwise convergence of resolvents in some sense. Here, some literature here, and there's also some work of two Japanese people, some older one. It's a bit hidden in their article, but they're also, this is all Moscow convergence, gamma convergence. This is all somehow related to strong resolving convergence. So my convergence is stronger. It seems to be stronger, more complicated, but actually in examples, it's actually sometimes easier to show. I don't need any limb subcondition or something like this. And the equivalence of the concept I showed you, well, there's an easy way in Weidmann's setting to define strong resolving convergence. You just use here the pointwise convergence of this object. And then you might use a similar idea as we did before to define some strong resolving convergence in the QE setting with this identification operators. This is some work in progress. Yeah, not yet done. And this would be also might be interesting to compare all these existing concepts on strong resolving convergence, including the PhD thesis of Sabine Bürkli. She collected a lot of results of Stummel and Weinko and these people, and it would be good to compare all these concepts, but this is not yet done. Okay, let me now come to the final point. This is actually what I'm working now. Well, all what I've talked before is just published 2021 in the Journal of Spectral Theory. And now, then we came to the point, okay, we have two concepts of convergence. We have here the Weidmann convergence for, let's now only take two operators, yeah, because we want to define some sort of distance, so no need to have a sequence. So we embed everything in a common Hilbert space via isometries. This should be an N here, sorry. And then, well, as you would do for some sort of Gromov-Hausdorff distance, you take the infimum over all possible configurations. So all isometries and all Hilbert spaces. Yeah, and then you get, we call it the iso from isometry of the resolvents. And recall they might act in different spaces, yeah? And even if they act in the same spaces, you have some more freedom here. And now dQE, I define the similar thing. If some delta Rn, R1, R2, J for contractions between J1 and J2. And here, this operator is just are the quantities we've seen before. Here's the resolvent difference sandwiched. And I take now the modified version because otherwise it doesn't work so nicely. So I have not only have square root here, but I have another resolvent here. Yeah? And the same dual thing here, the similar one. And again, the inf over all possible contractions. And now, so what is clear now? Of course, if the ISO tends to 0 for some sequence here, if and only if I have the Weidmann strong generalized norm-resolving convergence. Yeah, because I have a sequence delta n tending to 0 such that this operator norm tends to 0. And the same here for QE, yeah, in the modified version. Because I just put this in the definition of my convergence, yeah, or at least in the modified one, yeah. So this is really clear. But how are now these distances here directly related? Yeah, this is now the question. And our second main result is now the last one for this talk, of course. Let's assume self-return operators for simplicity here. And bounded operators are 1, R2. So now you see a slight change of notation. I don't need any more that these are resolvents. Could be any bound operator, but you can have the examples before in mind that R1, R2 are resolvents of some unbound operator, no problem. And then we have the QE distance, as defined before, is smaller or equal to the isometric distance, smaller or equal to square root of 3 the QE distance. So these are equivalent. Yeah. And also, if both operators have purely essential spectra, I think spectra here, and both contain 0, then I have equality of the isometric distance with the Hausdorff distance of their spectra. There is a version for general operators with discrete spectrum, but this becomes much more complicated. I will not go into detail now. You should wait for our hopefully soon version of this article on arXiv. We worked on this since a long time, but okay. And also, if the isometric distance is 0, if and only if the QE distance is 0, this is clear here from this estimate. And this is true if and only if the spectra of the operators agree, and separately for not only a set, but for the essential spectrum as set, and for the discrete spectrum as a multiset, so including multiplicity, yeah? This is clear because if it says one eigenvalue is multiplicity 1, 1, 2, there cannot be, this cannot work. And now we have, because of this estimate, here, that all the convergences, this Weidmann convergence, if and only if this corresponding metric or quasi-metric convergence, if and only if QE convergence and the corresponding metric convergence. So now we compare these results, and let me just very briefly, sorry, I'm a bit, maybe I should stress this more, but maybe in the next talk. What we do, the main idea is actually we're cheating a little bit because we let the hard work do by other people, yeah? Well, by Azov and Davis from 84, they defined actually some sort of unitary distance, which is some very natural thing as an isometric one, but we just don't take only isometry, we take unitary operators. Then you can, of course, leave out one unitary operator here. This, you can take it out. You only need one unitary between two spaces. And clearly, because unitary operators are subsets of the isometries in a common space, you have this inequality here. because it's an inf, yeah. And the other inequality, we do the following. Actually, Olaf and Davis, they define a so-called, we never heard it before, but we learned it from these papers, a so-called crude multiplicity function. What you do is, so let me just write something here, lambda spectrum. So if this is essential spectrum of your operator, and you have here a discrete spectrum, then you have here your function actually has values infinity here, and here it might have the corresponding multiplicity, let's say 1 and let's say 2 for these eigenvalues. Yeah. This is a definition here. You take the rank of the spectral projection, you let it shrink to 0. And now you can see these functions agree for two operators if and only if they have the same essential and discrete spectra, including multiplicity. This is clear from the picture here. And then Olaf and Davis define some sort of, I would call it Prokhorov distance, if I understand it well, for, actually this is not a probability measure because it has value infinity. This is a rather bad behaving measure, but nevertheless you can define something. You turn it into a measure by summing up over the sum here. And then you compare the function here, the measure here, for some interval I, and here the epsilon neighborhood here, and the other way around. And what they show is actually that this distance equals the unitary distance. Yeah. If anyone knows a bit about this, some other reference of this crude multiplicity function, please tell me afterwards, because we just learned it from Olaf and Davis, and at least under this name, maybe there are other names of it. And the main observation from us is now, how do we come from the unitary distance to the isometric distance? So we now assume that 0 is in the essential spectrum of both operators, which is a very natural condition. If R1, R2 are resolvents of unbounded operators, then always 0 is in the essential spectrum, because operators are unbounded, if and only if, yeah, the corresponding operators are unbounded. And then this crude multiplicity function, oh, actually, I want to show, no, this is true, but I want to show then that alpha Rn equals alpha, this I want to show here. And why this? These two functions agree because they can only differ. So my sandwich operator here has only maxima, if this is not unitary, it has an additional eigenvalue 0. But if 0 is only the essential spectrum, we don't have to bother whether it's finite or not. It's infinity here and also infinity here. So they agree. So we have this inequality here, and then we take some inf over all isometries and so on, and we get easily our desired inequality, the other one. Yeah, this one here. And yeah, this is the main observation why we can show the why we actually, the ISO equals this distance here. And actually everything is then described by this function. Just, yeah. Okay, this is how we, yeah, so I'm cheating a little bit. This is how we actually treat this here. And to do this here, I didn't give any details, but I showed you something in the convergence setting, and actually this the one here is similar as before, as a simple direction, and this one is the other direction around. There you have to, well, you have to write down a little bit, but the arguments are similar. I need again construct a parent space to use this nudge construction of this defect operator. It's a similar arguments. Finally, let me come. You see a square root of 3 here, and you can ask, is it the optimal constant? Well, can it be 1? So this is the final point now. So what we at the very end, we should have done earlier, we just try to calculate this distance. They're very difficult to calculate, but we try to do it for very simple operators. Let's say a number times identity. And then, well, the unitary equivalence is just clear, it's just the difference of the numbers. This is clear. And also this is equal to the Hausdorff distance. And for the ISO, well, this is funny because you allow some isometries you take the minimum of these numbers, and this might win against this one, especially if the numbers have different signs. Yeah, so this is not the same. It might be strict. It's maybe not optimal, but it has to be at least square root of 2 because of this number here. Yeah, so we cannot have this to be 1. And yeah, let me give the outlook. And I took more time than I thought. Actually, they're all quasi-metrics, and they somehow describe actually the operators up to, you only can distinguish them if they have different essential spectrum and a different discrete spectrum or different multiplicity. So of course they are not, I didn't say it here, but if the uni is 0, it doesn't mean they're unitary equivalent, because unitary equivalence is much stronger. You only have equality of essential and discrete spectra as multiset. Well, some results extend to non-self operators. I didn't mention it here to keep it simple. And as said already, you can use the convergence equivalence to do some strong concept for the QE setting. One might be interesting to do similar works on Banach spaces. One has to see what, instead of adjoins, one needs another operator maybe. And those of you who had talking me about this topic before, I usually do it with form domains, and then I have another family of operators respecting the form domains, and you need then to show how close are they to the original identification operators and so on. And it would be nice to define also some distance here. Yeah, this is not yet done. And I think my time is up. Here's some reference list, very incomplete. And thanks for your attention. Yeah.
So thank you for your nice talk. Any questions?
Yes, may I?
Yes.
May I?
Yes, of course.
Olaf, you said that you're watching the speed of convergence. So typically the quasi-unitary goes delta, as in our old papers, and the resolvent difference goes delta or sometimes delta square. But at one point you said that about old estimate and more clever estimate. And so it makes me thinking, is there a natural limit how far you can go with improving the approximation speed?
Well, what I didn't do yet is to use a new concept here. Where is it? Here. To use a new concept here for our old thick graph paper. Yeah. One might be able to get a better estimate here. But let me go back to maybe for those who don't know so much the details here. Actually, what we show here, this convergence speed delta n is of order epsilon n square root, yeah?
Mm-hmm.
And what actually one can show with different methods, like from Daniel Grieser and those, actually the spectra should be of order epsilon. This can be shown, yeah? So this would be the optimal constant. And this might be that using the new concept, one might be able to show right the way the good distance here, the right estimate. I'm not sure, but I have to check. Not your time. Or this might be because of, you know, our never-ending story about the Dirichlet case, where we need a more clever approximation operator. This might also help to do it here in the Neumann case. I'm not sure. Yeah, but
Well,
at
in
least
some cases, of course, you know that you're not ideal, like our 1/13 in the fat graph.
this is not
So
optimal.
then
Yeah.
you guess that 1/2 is optimal, but
Well, I mean, it's a little bit cheating, because once you know how, I mean, actually you want to know how the spectrum converges, but if you know how good the convergence speed is, then you know if your identification operator is good or not. It's a little bit cheating. It depends a bit what you want. If you know already by other results that something is true, you can see how good your approximation is or not. Yeah. But okay, this is how it is.
Thank you.
More questions, please? Oh, if not, let us thank all for the nice talk.
Yeah, thank you for your attention.
And we have 15 minutes break.
Okay.
Jussi, would you like to try share your screen?
Yes.
Yeah,
Let me
yeah, yeah.